Hello and welcome to another video in this series on Prolog. In the current videos, the recent ones and this one, we're exploring the idea of recursion, and today we're going to dive into it and look at it from a different angle and learn a little bit about arithmetic. So let's dive in with the motivating kind of question. So on the screen you can see there is a short list and it has 4 elements, and the question we're going to set ourselves is, how do we establish what the length of the list is? Now, just as a reminder, in Prolog we tend not to think procedurally, or we try not to. It does happen sometimes when necessary, but we start with a broad idea that we want to think about relations and properties that are true. So if we think about that, then we might have something like a property called len, or length, and a list, and maybe a number n, which is the length of the list. So this is true if n is the length of the list L. So that's the more kind of Prolog way of expressing this idea. The way we're going to solve this is through recursion, and it's not just because we're in the theme, it's the natural way to do it. So if we sort of said, well, taking it back to basics, if we just had a list of length 1, we could just unify that with a list with just a variable, because we don't care what the content is, and then we could say that is a list of length 1. And if we had one of 2, a list of length 2, we could unify that with something like this, and again that could unify with that, and that could unify with that. Don't really care what they are, and that we could say that's a list of length 2, so len 2 is true. But this is not practical, because we can't define these relations for lists of every length we might be interested in. We need something more general. Recursive solutions and recursive definitions are elegant, but they do require a lot of thinking. You have to have sort of super magical talent to be able to arrive very quickly at a recursive solution every time. For most normal people, we have to kind of write things down and sort of draw pictures to see if we can spot the recursive structure in a problem. So this one isn't too difficult. So what we can say here is the length, len lm, the length lm is, there's m. This is true if, and we're guided by the ideas that we found previously with recursion, that in recursive definitions we have a continuation rule and a termination rule, and the continuation rule is a definition of the property in terms of itself, but with one level or step smaller or closer to being resolved. So this, we can apply that straight away here. We can say that is the same as that with the head chopped off. So the head's chopped off, and that, so this length m is 1 plus this length here, or the length of the tail of m, of L. Can you see? Let's draw that again just to be really clear. So if I have a generic list there, let's call that L, and it's got a length m, and we know in Prolog, if we're not going to use extra libraries or other kind of add-ons, we want to just use the very simple core language. The mechanism we have for working with lists is to decompose it into head and tail, where that becomes the head of that thing, and the tail is then the rest of it. And we've seen that over the last 2-3 videos, so if you need a refresher, do go back or look at the blog. So if we're using this as a mechanism to work with lists of any length, we can say a length LM is true if the length of the tail, let's call that n, if that's true and m is n plus 1. So that's the relation that has to hold. This is true if this is true and the two lengths are related by this one being 1 more than the other one. So that's a continuation rule. We can see the definition is the same property. It's reduced the problem by one size, which we said several times is an important characteristic of a recursive definition. So this, repeatedly applying this definition, will keep chopping down our list until we get to 1 and then 0. So once we've got to an empty list, we need to say the length of an empty list is just 0. And that's just a fact, so there's no body there. So that's the termination rule, that's the continuation rule. So that's the general idea. I don't think that should surprise anyone listening to this. So that's what we'll try and implement. But what's new today is this idea of working with numbers and doing simple arithmetic. So I think it's worth saying a few things about how arithmetic works in Prolog. The first thing to say is that most languages that you've come across, whether it's Python or C or JavaScript or something else, many of them are quite suited to doing numerical calculations, some more than others, and most of them have the concept of integers, whole numbers, or real numbers with sort of decimal places after them called floating point numbers. If you're not familiar with the term, that's okay. With Prolog, from its original early design, its focus was not on being a language for doing lots of calculations. It's not something that you would say simulate the weather with, or write kind of neural networks in. It's a language that's much more symbolic, and it deals with more kind of discrete, concrete structures like lists and facts and things like that. You wouldn't use it to, say, calculate a fractal, which requires lots and lots of calculations with floating point numbers, those with decimal places. So it's not a language designed for that, but having said that, it is still useful to be able to do very simple arithmetic, like keeping a short count, for example. And we know, we've just discussed that the length of a list, it's 1 plus the length of that list, which is 1 plus the length of that list, which is 1 plus the length of that. So we want to be able to kind of add up some simple numbers. So just to say that Prolog, in its most common form, can do simple integer arithmetic. You can do adding, multiplying, subtraction, and so on. Some versions of Prolog will let you do floating point. So that's 3.2 plus 7.1, that kind of calculation. But be aware that in all languages there are methods, there are ways that errors can creep into this, because the representation of these numbers inside the computer is imperfect. One of the nice things about Prolog, actually, which we won't explore here, but useful to be aware of, is that many of them can handle another kind of number called a rational number, a fraction. So 1 over 3 plus 2 over 3, or even 4 over 3, and so on. So we can do that kind of thing and keep the answer in the form, so 5 over 3. So that's kind of nice, and it keeps it precise. That's just a nice little thing if you ever find it useful. So let's dive into doing some calculations, and let's do it by getting it wrong first, so that it shocks us into waking up and thinking, whoa, what's going on here? How does Prolog work differently to other languages? So let's look at some code. So we're logged into Swish as usual. If you need help with that, go back to the very first video or the very first blog. And on the screen here you can see I've written an expression x equals 2 plus 3, and in most languages that might give you x equals 5, most languages. Now remember that in Prolog equals is not assignment. It doesn't evaluate what's on the right and take its value and pop it into x. This is unification. In Prolog, equals is unification. That's so important, I'm going to write it. In Prolog, equals is unification. I can't shout that loud enough. Unification. That's so important. It's not assignment. Equals is unification. So we'll try to equate the two sides. So let's see what happens when we run that. It says x unifies with this thing called 2 plus 3, this kind of expression on the right. It's not 5. In the same way that you might say unification x comma 3 or 2. It's a short list. If I unify that with 5 comma 2, you can see more precisely what unification is doing. This is just a bit of revision. So here it's saying this can be unified with this if x takes on the value of 5. We've covered unification in an earlier video, and there's that blog that lists out useful examples, so do go back to remind yourself of that. So this is unification. So here x equals 2 plus 3 doesn't leave x as 5. So in order to nudge Prolog, we use a different instruction, x is, and that nudges Prolog to do the calculation. It encourages Prolog to look at the expression and see if it can evaluate it. It might not always be able to do that, in which case it fails. So that's how that works. Let's look at another illustrative example that highlights another issue. If I say x is 2 plus 3, actually let's just say x is 5. In fact, we can unify to x equals 5. It's the same result. And then we say y is x plus 2. What do we think is going to happen here? Let me make that clearer. So x is 5 and y is x plus 2. So this is a query, in fact, actually. It's saying, how can this be true? Remember, all Prolog queries are asking, is this true, or how can this be true? So how can this be true? Well, the first part of the query, there's two goals here, this one and this one. And the first one unifies x with 5, which is just true. It just succeeds. And then the second part says y is x plus 2. It's saying evaluate this thing and put it into y. So this is a little bit of procedural nature of Prolog, so just be kind of cautious around that. And the purity of Prolog is being compromised a little bit here. That's okay. We can forgive a language that's sort of decades and decades old. So x plus 2. Actually, on a more serious note, Prolog does sometimes break the purity, the kind of the declarative purity, and actually I think when it does it because it's practical and efficient. It doesn't do it without kind of without any kind of bad design behind it. So I think those cases where the designers decided to have a procedural element to the language, it was done for good reason. So here we have y is x plus 2. So how is that going to be evaluated? Well, x is 5 now. That's what it's been assigned temporarily. So that should be 5 plus 2 if we're evaluating it. So y should be 7. Let's see if that's true. Yep, x is 5, y is 7. Brilliant. That sounds like there's nothing surprising there. Now, here is a surprise. If I swap the goal order, x equals 5, now logically it's the same. We're asking the same question logically. So logically those two statements are the same. But let's see what happens if we run it. There's an error. Arguments are not sufficiently instantiated. This isn't particularly friendly, but what it's saying is that in order to, remember Prolog works left to right along its queries, along its goals. In order to evaluate this, x plus 2, well, it can't because it doesn't know what x is at this stage. So in normal logical Prolog, it would, you might expect Prolog to create a temporary internal variable to be filled in later, if it can. But actually with arithmetic it doesn't do that. It has a hard line that says either I can or I can't evaluate it now. So there's no delayed evaluation. So x plus 2 can't be evaluated now, and therefore that fails. So that's something to be kind of aware of, something to be cautious of. And it's so important, I'm going to write that again. So I'm going to write those two examples. X equals 5, y is x plus 2. And the other example was, I'll do it in red just as a warning, y is x plus 2 and x equals, or is unified with 5. Now this one fails and that one succeeds, and the reason is that this is first unified, so x equals 5 carries forward, and it's there, it's 5, so this can be evaluated. Whereas here we don't know what x is right now, and that's a very procedural aspect of Prolog when it comes to arithmetic. Now I should pause and say more recent developments in the last kind of few years have evolved Prolog's ability to work with numbers in line with its philosophy of it being a logical language, thinking about relationships, structure, constraints, and it's very natural to think about expressing constraints in Prolog, and you can explore that. Actually, we don't do that in this particular course because the aim of this course is just to introduce the key basics that give you the confidence to explore further. So one of the things you might want to explore after this course is constraint programming in Prolog, where you can define relationships which are constraints, like x plus y must always be less than 10, for example. So x plus y is always less than 10. And there's a way of expressing these constraints in more modern Prologs, including SWI Prolog, and then combining that with other facts or constraints and coming out with either a solution or a range of solutions, so constraint programming. And that's really interesting and useful, and it fits much more with the philosophy of applying logical constraints, defining logical relationships, and also allowing Prolog to not necessarily know the answer early in a query, but perhaps later. So that's kind of useful to know. Anyway, back to Prolog. So we've talked about this caution with arithmetic in Prolog. Let's now think about writing our approach to working out the length of a list in Prolog. So just before we dive in, let's remind ourselves of our recursive solution to this question. And we had a termination rule and a continuation rule, and we said that the length of an empty list is 0, and that's just a fact. And we then said the length of a list that relates it to its length L. I'm mixing up my terminology here, maybe I should call it that M. That's fine. A list and the length is true if another relation holds, the same relation here, but reduced by this by a step. So the tail of list and L, that's another one, M, that's true, and L is m plus 1. Those are the two things that need to be true. So let's write that in Prolog. And this is the example code you'll find online in GitHub. And it's very simple. There's just two rules. Same property len. And this the termination rule comes first because we want that to terminate first. Let's explain the continuation rule because it may look a bit unfamiliar. Let's start at the easy end. So L is m plus 1. Remember, is evaluates m plus 1. It's not is. It does not. It's not a unification. It's an arithmetic evaluation. The length of the tail is m. What is t? T comes from the head here, where you've seen before in the last video or so, where we unify the supplied list with the head and tail straight away. Now we could have done that like this, list, and then we would have to write in here list is unified with a head and a tail. So that could work, but we can do this in the head, so it's just a little bit more efficient. Now you might say, hang on, what's this underscore doing here? Now do you remember when we weren't interested in a parameter, or we weren't interested in Prolog reporting the value of a variable, we used underscores? So this underscore says, yep, you're going to unify the supplied list with the tail and the head, but the underscore tells Prolog that we're not interested in what the head is. Remember, we're discarding it and we're working out the length of the list. We're not saying if it's equivalent or equal to another list, so we don't need to look at the contents. So that should work. So the length, we're asking a question, remember, with Prolog, it's always a question. The length of the list A, B, C, is it 3? That's the question. And it's true. Is the length of that list 2? No, it's not. Is the length of that list 5? No, it's not. So we're asking questions. Is something true, or how can it be true? We can also say, how can it be true? We can say, L, how can this be true? It's true if L is 3. So Prolog will work out what L is based on this definition, and L is calculated recursively. L is m plus 1. And what is m? Well, it comes from this, which is the tail, and that's applied. This definition has then the whole definition then has to apply to the tail of the list. So you can see there's a chain of working out and keeping track of variables. If you want to know the work through that detail, I know we've done it before in the past and it's quite kind of time consuming, but I would recommend looking at the blog because it has a definition. It explains how that's done. So let's look at the blog there, and that gives you an example with a length of list 3, and it works through the detail of how it calculates that. I've chosen not to do it here because it will extend this video by another 10 minutes, but this is something that's so kind of fiddly in the sense of keeping track of internal variables. It's worth reading and sketching out in pen and paper, so I do recommend doing that. And why do I recommend doing that? Not because you need to know it at the front of your mind every day when you use Prolog, but knowing at least once how it works is useful because you then know how Prolog works inside, and you also can then write Prolog, better Prolog, more efficient Prolog. So let's see what happens if we did remove that underscore. If we run that, nothing really goes wrong, but Prolog does say, it gives us a warning and says, hey, you've got a variable h here, but you're not using it anywhere. Are you sure you've not made an error? So that's a good thing. You know, it helps us spot errors and mistakes. So if we put that in, we're saying, yep, we've thought about it, and we really don't want to know the value of that. In fact, I think if we just did it as an underscore, that would work as well. Yeah, that works as well. just like last time when we had the same property, are the two lists the same? Prolog actually does provide a property for doing that. I think in this case it's called length. Length. I'm trying to do this from memory. You can always look it up. A, comma B, comma C, and is that 3? Let's see. Yep, there you go. So length is something inside. See, it's an ISO, which is a standard Prolog, but we're making our own because it's a good exercise. So is it worth talking through that definition for the remainder of this video? So we've got a list of A, B, C, and the length of A, B, C, L, let's call it L1, is true if the length of the tail, which is BC, is true, and L2, that's L2 is the relation there, L2 is a variable, is true if L1 is L2 plus 1. And I'm using our variables L1 and L2, the definition will always remain the same, it just helps us keep track of what's going on. So then we need to work that out, or Prolog does as well. So len BC L2 is true if len the tail of that C L3 is true and L3 is L2 plus 1, and then that is true if the tail of that list is empty, and we can say we can call this L4 if we like, and this is true because the termination rule, and the termination rule is len empty list 0 is just true. So L4 is 0. I'm going to change colour so we can keep track of how the calculation happens. So L4 is 0 because of the termination rule. So that's just true. Oops, I've done something wrong there. So len the list of one item is L4, say, is true if the length of the empty list is true, and L5 is L4 plus 1. Now we can use the termination rule, because the termination rule says that this len termination rule says the length of an empty list is 0, so that unifies L5 with 0. So I'm using a different colour so we can keep track of the variables. L5 is 0 because of the termination rule. Now we can say L5 is L4 plus 1. My apologies, that should be L4 is L5 plus 1. I've made a mistake there, that should be L2, L3. Yep. So L4 is L5 plus 1, so L4 is L5 is 0, 0 plus 1 equals 1. That's L4. I've messed up the variables a little bit here, that should have been L1, L2, 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 L3. But you can see what's going on still. So we're saying that one is now 1. And therefore L2 is 1 plus 1 equals 2. L2. And therefore L1 is, remember L2 is here, so it's 2 plus 1 equals 3, and therefore that is 3. There you go, L1, L1. So that's just walking through. You can see I've messed up a little bit about naming the variables, but you can see the mechanism at play, how it's done. So I hope that's useful. Worth kind of taking a pen and paper and going through it properly with the blog, where I've taken care not to make any errors in the naming of variables. But it's useful to kind of see how that winds and then Fantastic. So not a long tutorial this time. And And I hope that's kind of given you a new dimension to Prolog, which is working with arithmetic, and how we can apply it in things like recursion, which is quite common. This kind of pattern of increasing or decreasing something in a continuation rule is quite common. Fantastic, great. We'll see you next time. Bye.